My name is Ryan Glusic. I've been working with Dr. Parker for the past year, studying the parameter convergence in the calculation of material vibrations. So the vibrations in materials make up many different properties, and the choice of the parameters affect the thermal and electrical properties, for instance. So, and I mean, this is a very fundamental thing to be known in the study of materials. So the convergence of these parameters, they directly affect the accuracy in our predictions. So in this presentation, I will first kind of go through the electron interactions governed by the laws of quantum mechanics, and the theory that we're using to examine these properties and the vibrations, known as density functional perturbation theory. We will test it on a semiconductor and a metal, and then we will eventually show how it works on an insulator, which we're still in the process of doing that. Next slide, please. So well, first of all, we have to study, or we have to understand the way electrons interact with each other. Electron-electron interactions make up many properties for materials, just the same way as vibrations are very important in the study of materials. The electron-electron interactions tell us about the chemical bonds and, like, as I said, the thermal and electrical properties. In particular, we kind of understand this information from the Schrodinger equation in quantum mechanics and the wave equation. Now, traditionally solving the Schrodinger equation, especially for many electron-electron interactions, is very challenging. So we use a theory known as density functional perturbation theory, which ends up with, you have to deal with a lot of approximation. I should mention this theory in particular is a computational theory. So you sacrifice some accuracy for simplification. And particularly, if you want a better accuracy that matches percentage change in, say, the total energy, or even matching experimental predictions or results, you have to be careful with your choices and parameters. So the advantage of this is that you can do this with many, many electrons in a simulation, whereas that might be difficult in the lab. Next slide, please. So a little bit about density functional perturbation theory. It is a kind of a cyclic pattern where you start by taking a kind of guess for the density of the electrons, or the orbitals, which is where the electrons should be for particular materials. Picture a nucleus, and then I'm sure all of you kind of have a general idea of a nucleus. So picture a nucleus with electrons around it. The orbitals are where specific electrons are located. So we start by taking a guess for the distribution, or the orbitals. We then perturb the density with displacements. So we take a whole bunch of minor perturbations or disturbances, and then when we sum all of those up, we get the thermal and electrical properties. And like I mentioned, this is a cyclic property. So based on the tunable parameters that we set, we can keep going and going and going until we reach a kind of determined convergence in the set. Next slide, please. So here's our initial results so far. We've looked at two different types of materials, one being an insulator, one being a semiconductor and a metal, particularly silicon and aluminum. The figure on the left represents the electronic sampling mesh or reciprocal sampling mesh. Basically, if you wanted to visualize this, you can think of a three-dimensional density or grid of points, particularly their vectors, but you can think of them as a grid of points in the simplest case. And as we increase that, as you can see in the figure, we approach a more, we approach zero in terms of a percent change for the total energy. It's a little hard to see in these figures. We are still in the process of generating data, but it's you can see that as you increase the density, you get a closer and closer, more accurate result. In the second case, we have the wave function cutoff energy, which is similar to a grid of points, but it's more for the wave function, which is more of a basically the number of sampling points you're going to have in calculating that wave function, which it's related to the Schrodinger equation. And without going into too much detail, a larger value represents a higher, more accurate result. And then it's very similar for the vibrational reciprocal sampling mesh. The difference between the left figure and the right figure, well, for one, I only have the silicon results for the right figure, but it's there's two aspects to it. The one on the left is electronic, and the one on the right is strictly for the vibrational aspects, which is a second tier to the previous cycle that I was mentioning. So far, it's only two materials. We plan on adding an insulator. Next slide, please. So right now, we're in the process of testing an insulator, and we're testing many more parameters. Our goal with this is ultimately to provide a guidance on parameter choice using this theory. I believe I mentioned that the reason we would want to use this theory, or anybody would want to use this theory, is that it kind of makes predictions on what particular aspect is deemed important when calculating, rather than doing this in the lab. You have a lot more leeway with computational aspects than you would physically doing this in the lab. We have many additional parameters to be testing, and we hope to have further results soon. And thank you for listening to me.
Great, thank you, Ryan. Does anyone have any questions for Ryan? If so, please feel free to turn on your camera, unmute yourself, and go ahead.
Ryan, can I ask you a quick question? More really, I think, a clarification.
Yes,
if we can go back to the slide with the graphs with the results. You said silicon and aluminum are the materials. It's not obvious. The labels are a little hard for me to read on my computer. Can you tell me? So is it silicon on the left and aluminum on the right? Or
yes.
the left and middle graph? And then
yes,
what about, and what's going on with the farthest right, the sampling graph?
So the farthest right graph is silicon alone, as I did not have enough time to produce the aluminum results.
And so what are the top and bottom halves of that figure?
Yes. So the bottom half represents the absolute value of the relative change between the energy levels, whereas the top half is just the relative change.
Got it. Okay. Is there a reason that the absolute value is important rather than the actual value of the energies?
I would argue that you can kind of see the trend. It's a little bit easier to see the trend in the absolute value, I think, as it kind of goes down towards.
So in terms of convergence?
Yeah, exactly.
Okay. Okay, cool, thanks.
Thank you.
I have a question, Ryan. I mean, I know what the answer is, but I'm not sure if I heard you say it. Did you say what the meaning of delta R was?
The relative change. Yes, I realized that.
Relative change of what from what? That's
the relative change. Yes, the relative change from the frequencies that we determined, as explained in, I believe, the last slide, where you take the very highly converged frequency and you compare it to these changes as you vary the parameter, and that shows the difference or how close the other frequencies are to a very well converged frequency.
and how many frequencies roughly were sampled for a given single point on the graph?
For singular points, that would be, I believe that would be, I think it's 8 for silicon, and it should be 6 for aluminum. I can't recall off the top of my head. Either that or it's 4 for, no.
So it's just one branch on the,
You know, it's a sum of all the branches.
okay. And does each branch have like 10?
I'm sorry, your mic is kind of.
Sorry, how many points are sampled? How many frequencies are sampled on each branch?
I believe it is 10 per each one.
All right. Well, thank you, Ryan.